Okay, well, good morning to the second presentation in the GSM track. This is a presentation about OsmocomBB, which is an open source baseband firmware for a mobile phone that you can use for, among many other things, for security analysis. This time not so much analysis of telephones themselves, but analysis of actual network equipment. Let me just start. Well, I'm skipping the slide about myself. You can check that out if you're interested in some later point. Let me make a general observation. They turned it down because it was generating noise. So, okay. Now, the general observation is, well, both the 3G and GSM specifications as well as the TCP/IP protocol specs are publicly available. Anyone can read about it. Anyone can learn how the system works. Anyone can, understand what is the possible attacks, what's the security situation with these protocols. And if you look at the internet world, where we have Ethernet, Wi-Fi, TCP/IP, and so on, that protocol stack receives a lot of scrutiny. People are playing around with it. How long has it been since people have been sending Christmas packets and the ping of death and those kind of things, right? It's a long time ago for people in the IT security community. And GSM networks are just as widely deployed as the internet, but we don't see the same level of scrutiny on the protocol level happening. And the primary reason for that is actually that there is no such thing as an Ethernet card for GSM, right? A simple transceiver that gives you access to the physical layer, but which allows you to send any arbitrary data on layer 2, layer 3, and the upper layers. That kind of device just did not exist, and I'm not aware that it existed commercially, and particularly it did not exist in any way that people could just go out there and buy something like that. It's impossible. So all you could buy is a phone or a network equipment, but you could not buy something that gives you access to the lower layers. And the reason for that is that the industry involved in these products is, from my perception, extremely closed and sometimes closed-minded. There are very few implementations of the protocol stack, right? A couple of companies did that initially, and then lots of other companies bought licenses to that code. So if you look at how many TCP/IP implementations we have, there's many more than you would ever see GSM protocol implementations. And the chipset makers that produce the components that are used both in the base stations as well, even more so in the telephones, they don't release hardware documentation in a way that other companies release hardware documentation about their silicon. There are very few companies that build the baseband chips that are used in those phones. The companies, as I said, they're mainly silicon companies. They buy an operating system kernel from somewhere else. They buy a protocol stack from somewhere else. So it's not like their core, at least initially, it's not their core expertise, that stack or the operating system. And the way how the traditional business model in that industry works is if you want to buy baseband processors from one of the manufacturers, you have to become a customer. And becoming a customer for such products is actually a very tiresome exercise. It starts with having to put up a large amount of money on the table and committing to hundreds of thousands at least. That's already a very small customer, typically millions of units per year in quantity. It's not a component that you can just go to an electronics retailer and buy. That's not the case. So if you look up the websites, there's very few public information about these chipsets available on the manufacturer's website, and it always says, for selected handset manufacturers only. This is not a product we're selling publicly. And on the network side, not many companies actually build network equipment, right? Today, significant really, there's only Alcatel, Lucent, Ericsson, Nokia, Siemens Networks, and Huawei. There are a couple of other companies, but this is really the companies that own the market. And some operators buy equipment from them, but only operators are customers. So again, you cannot just go there and buy equipment. It's not like you call them up, say, you know, oh, I want this BTS model, and they say, okay, sure, we ship it next week, right? You have to, this is a long process, you have to set up a relationship, you have to sign all kinds of agreement, and so on and so on, and then maybe if you're interesting enough, you can become a customer and you can actually buy equipment. And the minimum number of, the minimum amount of money you need to put on the table to buy a minimal GSM network is in the order of hundreds of thousands to millions of euros. And even a single component, which is not sufficient to operate a network, will cost you, 10 to 40,000 euros. That's definitely not something that will encourage academic research or will encourage independent research into the security of those systems. Also, if you have that equipment, how do you use it for security analysis? You can then run a network and you can make phone calls, but that's not really what you want to do. On the operators, well, operators are marketing and finance. Typical operators today outsource not only their network planning, network servicing, network deployment, but they also outsource the billing. So this really only leaves marketing and finance left over. There are exceptions. I'm sort of exaggerating here, but there are operators where it works exactly like this. Also, the staff at the operator, the technical staff, they mainly know the equipment as it is shipped from their supplier. They get some training courses from the supplier, and they know, they have system administrator knowledge, but they don't have the knowledge that a developer of the system would know, would understand the details of the protocols and so on. So you end up having very few people, even at the operators, who know the protocol beyond the user interface that the supplier gives to them. Which I think is fairly dangerous. And especially since they're outsourcing more and more, they become a complete, I don't know, how can I say, a complete slave of the equipment manufacturers. Now, if you look at this entire situation, right, the implications for security are, well, we have almost no people who understand the protocols who do not work for one of those few companies that implement the system. We have very little independent research. If there is research at all, it is cryptographic or theoretical, or on a much higher level, mobile malware. It's like 7 to 13 layers up from what I'm thinking. So that's really in a different world. And we don't have any, or we didn't have any open source protocol implementations when we started out with all this, which means nobody could do any practical experimentation, right? I think the open source implementations that we have in the internet world of all the protocols that are run on the internet are key to enabling all the small and medium-sized companies, the individuals, the students, the academia, to actually have some ideas, implement them, test them, innovate around those protocols. But in the GSM world, this is restricted or has been restricted to the couple of big players that are inside that industry. And that may also very well be a reason why the security has not been improved significantly over all that time. Because it's just these companies and they make a lot of money of shipping their existing technology, and why would they change it? So if you want to start with protocol level security analysis, there's two sides. You can get started on the network side. I don't want to talk about this today. We did this with OpenBSC. I presented about this last year at DeepSec. Now, on the telephone side, so what do you want? You want a telephone that's under your control. You want to receive and transmit arbitrary data on arbitrary frequencies at arbitrary points in time. It's relatively difficult since the firmware of those systems and the protocol stacks are closed and proprietary. And let me add at this point, right? It doesn't matter whether a telephone runs Android or Windows Mobile or something like that. This is running on a different processor. I'm not talking about the application processor here. It doesn't matter whether the application processor runs open source or closed source or God knows what. The baseband processor in all the phones that ever have been shipped is completely proprietary. Well, so if you were to set out to write a protocol stack, right, you have the specification, you can just code all the stuff according to the specification, but in the end you need to interface some real radio hardware, and that's sort of difficult if you don't get the documentation to do so. And to say that is, in many cases, the cell phone makers, the companies that create the actual device, they do not even get that level of documentation from the chipset supplier. Because the chipset supplier, well, they sell a bundle out of their firmware, their software, their stack, and the silicon. And the documentation that a cell phone maker gets is related to, well, maybe how they can interface a different user interface to the phone, or maybe how they can interface a different, different RF transceiver or different antenna switch or something like that, so electrical changes they make in the board. But they do not get the documentation on how they can write their own stack and run it on that hardware, which is something that no cell phone, well, with the exception of, I have heard RIM, but no other cell phone manufacturer really does that kind of stuff. So the documentation typically is very, very restricted and kept among very few players. So there have been a couple of attempts in the past. There was the TSM30 project, a part of the THC GSM project. That's probably 5 years, 6 years from now. And MadOS, which is even earlier than that, which was an alternative operating system for old Nokia, 1990s Nokia phones of a generation called DCD3. MadOS was very, very promising, but then was abandoned at some point due to, I don't really know, maybe lack of time by the people who were working on it. They were already reverse engineering the shared memory protocol between the baseband CPU and DSP, and it was really, really advanced, but stopped at that point. Now, okay, so to bootstrap sort of this process, you read the specifications, you gain knowledge about the protocols, you obtain actual equipment, you try to get actual protocol traces, you implement the protocol stack, and then you play with the security of the protocol. And we are already now, after the work that we've been doing, we are at the finally step, right? So this is a presentation that tells you we now have the tools, it's up to the security community to go out and use those tools now. If we look at the GSM network, the classic GSM design looks like this. Today's networks internally look very different. But what we are talking about is the telephone here, right? This element, and the the air interface between the base transceiver station and the telephone. It's the same interface that air probe is sniffing, right? And we're now talking about generating that interface from within the telephone and implementing the protocol stack. And the protocol stack that runs there, there's a layer 1 that runs, of course, only until the BTS, until the antenna. There is a layer 2 that's also terminated here. But then there's a layer 3 that goes to the base station controller or to the mobile switching center, depending on what you do. So if you can manage to implement the layer 1 and layer 2, you can send transparent messages to the base station controller, which controls dozens to hundreds of cells. Or actually into the mobile switching center, which operates, a large city or half a country, depending on the size of the country. So typically in Germany, for example, each operator has at least one MSC for every major city. This means you can transparently send messages to that equipment. Now the question is, how much has this equipment ever been hardened against malformed messages and that kind of stuff? So you have an interface, an air interface that's public, that's everywhere, that's ubiquitous, and it gives you the ability to directly send messages deep into the core network of the various operators. The names of the individual components, I'm going to skip them. That's, if you want to check them out at some later point. The interface that we are talking here really is the interface between the telephone. MS means mobile station, it's not Microsoft. And the base transceiver station, the BTS. This is the antenna and the transceiver associated with that. And one thing to understand when you talk about GSM is that it is not a symmetric network. It is not a peer-to-peer network. It is not an end-to-end network. It's a very asymmetric, very distributed network where you have different protocol stacks in each of those interfaces. So the protocol stack that you will see here, the protocol stack you will, what's going on here? What's going on? The protocol stack you will see, I'm not supposed to be touching my mouse pad. The protocol stack you will see on the air interface is completely different from what you will see on this ABIS interface, again completely different here. And could not be any different than the interfaces you see here and the protocol stacks here. So they're completely different protocols, different encoding, different messaging, different stacking, and so on. So there is no one GSM protocol. There's individual protocols that are layered on top of each other at different points in the stack. Okay. The other thing that you should remember when you start to get into GSM is that you do not have messages that contain source and destination addresses. It's not IP, it's not Ethernet where you have a source and destination address in each and every message. It's a time division multiplex architecture, and if you don't notice, if you don't track or trace who has established a certain channel, then you do not know afterwards all the messages inside that channel. You don't know where they are from and where they're going to. So it's like a telephone call, but even only for the signaling, like a telephone call where the telephone call setup shows you, what's the number that has been called and so on. But in the actual, voice conversation, of course, you don't see anymore who is sending the data and who is receiving the data because it's implicitly known by the state of the various endpoints in the stack. This is the stacking that you find on the interface. There's a layer 1 radio layer. The TS numbers give you the technical specification. So if you want to learn more about these individual layers, these are the specification numbers that you should be looking out for. Layer 1 is the radio layer, relatively uninteresting for anything but denial of service attacks. Layer 2 is LabDM, which I also believe is fairly uninteresting from a protocol level security point of view. But where you actually get into is the layer 3 messages. And it's actually 3 sub-layers to layer 3, radio resource control, there's mobility management, and there's call control. And then you have other the question is whether it's really for layer 4, there's no clear definition, but there are other things that are on layer 3 and higher, which are for SMS transfer, for USSD, for location services, and so on. And I think layer 3 and above is really where you want to focus on for protocol level attacks and such. Of course, there's a number of known problems of GSM. Just a very quick recap, right? We have no mutual authentication between the telephone and the network, so the telephone can never know whether it's connected to a real network or not, which leads to rogue network attacks, man-in-the-middle attacks, enables IMSI cachers. We have weak encryption algorithms. The encryption is optional to be even worse. We have denial of service on the random access channel, and we have strange protocols by which the network, which is not authenticated, can inquire the telephone about GPS coordinates. This is conceptual security and privacy and confidentiality problems in the specification. There are more. Sylvain Mounon has just presented yesterday about the IMSI detach attack and other things. But what I want to talk about now is not so much the conceptual problems. Of course, you can also experiment with them, but implementation problems, of course. Now, in order to understand what OsmocomBB is, we have to look a little bit of what this baseband processor is. It's typically an ARM7 or an ARM9 core. In all the GSM and GPRS and edge-only phones that don't implement 3G, you will very likely find an ARM7 core. ARM7 means there's no memory management unit, thus there's no memory protection, no non-executable pages, and so on. You run some real-time operating system on that ARM7 core, and next to the ARM7 you have a digital signal processor, which is the code that runs on that, and the type of DSP is really, really proprietary and specific to the baseband chipset manufacturer. That's also where, in a peripheral to the DSP, the A5 encryption is implemented. The software stack that runs on this baseband processor is written in assembly and C language, of course, lacks modern security features, and I think we will hear more about this later today. Now, a baseband chipset roughly looks like this. This is a very traditional GSM baseband chipset design. You have the digital baseband processor, that's your DSP and ARM7 core, has some mask ROM, UART, SPI, I2C, typical microcontroller type design. Not very different from, if it wasn't for the DSP, it would be your typical ARM-based microcontroller. You have an analog baseband, that's basically the analog digital converter, digital analog converter. You have a transceiver, mixer, and VCO component that actually down converts the radio frequency into the baseband and vice versa. You have a power amplifier for transmitting at typically up to 2 watts in modern day handsets, and an antenna switch, and various control lines between them. Now, when we run our own software on a baseband processor, the software will run here and will drive all these peripherals over here and will implement to receive the radio signals or transmit signals, and you will implement the protocol stack on this digital baseband processor. So what we need in order to do what we want to do is we need the telephone under our control, we need a layer 1 that we can control, we need layer 2, layer 3 that are in control. None of those components existed in open source or a freely available manner until this year, so we needed to create them, and this project was started only in January this year, by the way. So there's different ways of how we can address the problem. We could build our own custom hardware, but then we need to go through hardware prototyping and so on. So it's a bit cumbersome. So instead, there's two ways how we could do this. We could use an existing baseband chipset, or we could use general purpose components, but we did not choose to go down that way. We were already very far in sort of designing what kind of architecture we want, and we actually already bought prototyping boards, but then decided finally that we'd rather go for a lazy approach. And lazy means we use existing mobile phones, we know the hardware works, we know they don't need to do any hardware prototyping, we don't need to go through hardware revisions. We can benefit from the economics of scale, since those phones are manufactured in large quantities, no custom hardware, so it's really, really cheap. And we have, in the end, more time to focus on writing the protocol software rather than doing hardware design. So we searched for suitable phones which should be as cheap as possibly, as widely available as possible, so most people can obtain them. Should be old in order, or simple in order to keep the complexity of the software low, and there should be a lot of leaked information about the baseband chipset. So what we found as a primary target is the Texas Instruments Calypso chipset, where the digital baseband documentation is on Cryptome. Analog baseband documentation you can find on Chinese developer websites. And the source code of the proprietary GSM stack for that, for that chipset was available on SourceForge for about 4 or 5 years, and thousands of people have downloaded it before it was finally taken down. So the source code was not used, we did not copy any of that code in our project, but however, the source code allows us to fill in the gaps in the documentation that we had, to understand better what the hardware does and how it behaves, so we can program it from our own code. There's another series of chipsets which is extremely popular in recent years, is the MediaTek MT622X chipsets. There were 95 million of them produced in the first quarter of this year. It's a massive quantity. Those chipsets are used in very, very low price phones sold all over Asia. This is our second idea, but we don't have any support for that yet. So the initial choice was the TI Calypso. We started in January, we implemented the baseband software, layer 1 through layer 3, the hardware drivers, and so on. We also want to have a simple user interface on the phone, but that point is not there yet. So points 1, 2, and 4 are there, point 3 is missing. The project name means Open Source Mobile Communications Baseband, if you ever wonder why that's such a strange name. The software architecture, well, we reuse existing code from OpenBSC whenever possible. We run as little software in the phone as needed, which means we only run the layer 1 in the phone, and we run layer 2 and layer 3 and all the application logic code inside the PC, on the PC, and have an interface between them. Going to skip that interfaces slide. You can read up more if you're interested in that. So the firmware that we download, that we developed in C, compile using a cross-compiler for ARM, and download into the device, contains drivers for all the different components in the phone, including the NOR flash, including the LCD that you can display something on the phone, but of course, primarily all the GSM-related components in the device. The software we run on the host is called Layer 23, and it uses what we call Layer 1 control interface to control the Layer 1 inside the telephone. But both the software on the host PC as well as the firmware are both entirely written from scratch. It was no code reused that came from anywhere else, and it's both open source software licensed under GNU GPL. The hardware we support, well, it's mostly this TI Calypso Yota Rita chipset, and there's a number of Motorola phones that were manufactured by Compal Communications in Taiwan. which is C110 to 119 and a C120 to 129 and so on. So basically anything that starts with C11, 12, 13, 14 and 15 will be supported by our hardware. Most of the development happens on the C123 and the C155. The C155 looks like this. You know, it's a very, very small, low-end phone. It doesn't even have any USB or serial connection. It just has an earphone jack, and we actually download the software through the earphone jack, since that's not only an analog audio interface, but also has a multiplexed serial port on it. Interestingly, right, downloading software on those devices is extremely easy. You just press the power button, and after you press the power button, it tries to negotiate with some host software. And if there is some host software, the bootloader that already is in the phone as it ships from the manufacturer will download the executable code over the serial line, and it will jump to it. Right? It couldn't be any easier. There's no protection whatsoever. There's no digital rights management, no cryptographic signatures, nothing. You push the power button and it will, you know, happily download any code that you send it. Okay. If you look at the phone PCB, you remove all the shielding covers. It looks like this. Unfortunately, we have way too much light in front here to really see what the projector is projecting. Yeah, so these are the individual components. You can easily find what's in the block schematics. You can find here again the digital baseband processor, analog baseband, RF transceiver, power amplifier, antenna connector, and so on. So this initially we had to take a couple of them apart to be able to put, you know, solder wires onto the individual traces and do measurements and get the layer 1 and the drivers up and running. Now, what is working? We have hardware drivers for basically anything. We have a layer 1 that does all the main tasks of a layer 1, power measurements, the various synchronizations to carrier clock, bit clock, TDMA. We can receive various bursts and we can transmit them, of course. We have automatic gain control. We implement frequency hopping. We drive the encryption accelerator or encryption implementation hardware that exists. We have a layer 2, layer 3. We have cell reselection and so on. So starting from August this year, it's possible to do voice calls with OsmocomBB. It does the various, if somebody has background about GSM, supports the various assignment schemes. It supports authentication using a SIM card. It has support for the FR and EFR codec. What we don't have is neighbor cell massive measurements, which for security analysis are completely unneeded. We don't do handover, which typically you also are not very interested in if you want to do security research. We don't have a user interface on the phone, but all the user interface is command line based and runs on the PC. We don't do circuit switch data, we don't do GPRS, and of course there's no type approval for this stack. Okay, now I'm going to leave that executive summary slide as well. I mean, you can read that some other time. What I'm going to do a demo quickly, so I just want to finish with the slides. Right, the GSM industry has been making security analysis very, very difficult, which, well, some people can say is a security feature, right? Security by closeness and obscurity. But of course, what we have done with this mobile phone, anyone could have done 10 years or 15 years ago with a mobile phone back then. There's nothing new. There's no new development. There's not really nothing that has happened in the last 10 years that suddenly made this possible, right? With something like AirPro, advancements in software radio architecture and so on really have made this possibly new. Or the key cracking, right? With the computers 50 years ago, it would not have been possible in a feasible amount of time. But this, running custom code on a telephone, could have happened anytime. And maybe it has happened any time ago, but nobody has ever publicly talked about it. We don't know, right? So, okay, now we can send arbitrary data into a network from the telephone into the network. So right now this means the basic tools for starting to fuzz mobile networks are available. What we don't have is any nice interface or integration with fuzzing tools like Scapy or any kind of other security tools that allow you to send messages handcrafted. But yeah, I think TCP/IP security is boring for at least 10 years. Try to do something else. You know, look at GSM, look at other things, look at RFID systems, look at DECT, look at Tetra, look at all kinds of communication systems that are out there, but not the internet and not TCP/IP. It's, you know, people have been doing this for way too long. Anyway. Okay, so some thanks to a couple of people who've been very, very much involved in this project. Dieter Spar, who is here, Andreas Eversberg, who is not here, Sylvain is also here. So this is really a team effort. A lot of people are very dedicated working on this project, and yeah, my thanks for that. If you want to read more, there's a couple of links. And now let's turn to a short demonstration. So, I know the font is too small. Just give me some time. Why is this not? There we go. Huge. Okay, now what I'm going to do is I'm going to the right directory. I'm starting what's called the OsmocomBB project. OsmocomBB is the open source mobile console program, where I can say -MC155, this is the telephone I'm going to use. I'm saying -P, that's the port, the serial port that I'm going to use, and I'm going to specify which firmware that I want to load. Port compile E99 layer1.ramload.bin. Okay, now I have started a program that can talk to the ROM bootloader in this phone. So this basically, as I said, when I press the button, it starts to suck the code into the telephone. Yeah, doesn't always work as reliably as I want. Yeah, but now it works. You see, it's loading 40 kilobytes of object code into the telephone, and this hello world and whatever we see here is now executing from the baseband processor in this telephone. We also see layer1.bin in the, you probably cannot read it, it's too small, right? But it displays layer1.bin in the screen, which tells us that the layer 1 firmware has been downloaded into this. The firmware that I download, as I said, is completely available in source code. I just compiled it in advance so we can have more exciting things in this demonstration than watch GCC compile code. Okay. Now, let's open another window. I'm going to the right directory again. Why is it not source-misc? Okay. Okay, I'm doing one more thing before I'm starting this. I'm going to start a don't need sudo for that. I'm starting a Wireshark instance, and I'm going to listen on the loopback device, which is very interesting, right? I'm capturing on the loopback device. And what I'm going to do furthermore is I'm going to start the, this is not what I want, what is it, -I. I always forget the command line arguments. Oh, and it's not working. Okay, let's restart the phone just to be sure. Oh, come on. I don't know what's going on. Sorry for that. It was working 2 days ago. The PCCH scan was working. Yeah, somehow it is not Any ideas? No.
Do you use the correct version of the firmware?
Yes, I think so.
Because I thought we didn't use the RAM loading, but the other.
Ah, yes, that is completely true. It's my mistake. Yes, I was downloading the wrong firmware image. It's not a surprise that it didn't work with the wrong firmware. Thanks for somebody who's paying attention. Should still be in the history. Yes. Okay, that's fine. I hope this will be working now. There we go. There we go. Okay. So now I'm starting this scan. It's scanning over the GSM. Oh, nah, the projector. It's way too bright for the projector to have any decent contrast. It's scanning over the frequency band, and it's identifying all the various cells that are there. It's receiving the broadcast messages from various cells. You will see lots of 2B again here, right? It's the same kind of messages that Carsten has been showing. Now we're seeing them from a phone. If we look here, in this Wireshark instance, we see the real-time messages that the telephone receives from cells. And we see all kinds of messages that are going on. For example, here we see a system information type 2 that indicates the neighbor channel list. We see system information type 4, which sort of tell us what is actually the cell is. This one is a T-Mobile Austria cell that is received here. This is not just in a receive-only mode, but as much as we can receive messages from the cells, we can also transmit messages, we can establish channels, and so on. I'd rather take some questions than do some more demonstrations right now. But if you want to play with this, you can buy these phones for about 15 euros on eBay. If you cannot find one, you can contact me. I have a couple of them in stock. The cable here costs you something like €1.50 to €4. This is the USB to earphone connector cable, which has a serial converter inside. So the entry barrier to play with this is really, really low. It's mainly you need time, you need to give it some thought, you need to try to understand GSM, and you need to invest something like 20 euros in equipment. Okay, questions?
Any questions?
No questions. There is a question.
Yeah, any interesting tests with also sending some nice testing packets towards networks?
Yeah, well, I mean, I'm not sure if you've seen Sylvain's presentation yesterday. He was using the very same software to send his IMSI detach messages, right? So there's this sort of conceptual problem in GSM that if a telephone is switched off and it tells the network, I'm switched off now, this message cannot be authenticated in the protocol. It's not, there's no means of authenticating this message. So if you know somebody else's identity, his IMSI, you can just detach him from the network by sending such a message. So he's using OsmocomBB not as a phone to make phone calls or something, but he's using this as a layer 2 sort of transceiver thing, and he can send this message to the base station controller, which then, no, actually, it goes up to the MSC. This message goes to the mobile switching center, and it will mark this other person, this other telephone, as no longer being on the network, so any incoming calls will fail at that point to the subscriber. So this is not a malformed message, but this is sending a well-formed, as it is specified message, but sending it from a phone that would that is not the phone that you're actually detaching. So you're detaching somebody else from the network. I've done some tests at operators where I have been invited, and I've managed to, with sending custom crafted messages, I cannot say where it was, but yeah, I managed to crash base station controllers. I haven't really had any chance to experiment with mobile switching centers yet, but at least the BSC was definitely possible. And that was not even intentionally trying to do something, right? Now, crashing something is just a denial of service attack, of course, right? More interesting is trying to exploit things, which I believe in the case of network equipment is much more difficult than in the case of telephones. I mean, we have people like Ralf Philipp Weinmann, who will present later today, I think, showing us how to exploit the telephone. Because in the telephone, we have a processor and operating system that's sort of known. It's an ARM core, and it runs Nucleus or L4 or something. But in the carrier-grade equipment, very, very few people actually know what the hardware architecture looks like, what kind of programming language or runtime is used on those systems. You know, almost nobody has access to firmware or software running on these switches and other equipment. So I think implementing a working exploit on those systems without detailed insider knowledge of the technology will be relatively hard. There's another question.
So what is the legal status of experiments like that? So especially regarding contacting the operators from the operator side, and on the other hand, regarding the national regulators of frequency bands and networks.
So the legal situation in general, I'm only very familiar with the European and specifically the German legal situation, and the situation is like this, that there's a couple of criminal offenses that could apply. One of them is, for example, interference with public telecommunications networks is a specific offense listed in the criminal code, and is punishable up to 5 years of imprisonment. So interfering with public networks is definitely something that is under a very high penalty by itself, right? Just interfering with the network, even without, you know, accessing any information that you shouldn't have access to, that's a separate offense. But just interfering with a public network has that kind of penalty. So the kind of tests that I've been doing either against my own network, of course, which is not a public telecommunications network, or at an operator where we actually had permission in the lab to do those kind of things. So if you do this on a public network, then yeah, quite certainly you will find a criminal offense, not even speaking of the civil offenses that you commit, probably violating the terms of service of that operator and those kind of things. Modifying the firmware on the device itself, I don't see any legal problems with that. The regulatory requirements at least in the European Union, the harmonized regulatory requirements regarding telephones, they apply for people who sort of bring devices into the market, people who import the devices, people who sell the devices. But there's no regulation about people who produce alternative software for devices. It's just simply completely unregulated. There's currently a poll by the European Commission on how they should deal with those kind of things in the future, but so far there are no regulations regarding that. So if we as the OsmocomBB project release that software, I don't see any problem with that.
So it's possible to use that against your GSM gateway? Your GSM
of course, if you run your own network...
There's no certification for the mobile phone software.
Well, there is certification, but the certification applies to people who ship a product into the market. And if you buy a device that is unmodified from the market and you do modifications yourself, then there's no regulatory framework surrounding that. That's my understanding. And of course, if you run your own GSM network, you will have an experimental license of some sort anyway. And then, of course, you can use your telephone, even if it's a modified telephone, with your network, right? As long as that telephone does not cause interference with other operator networks. So if you're confident in the code that it doesn't interfere, and that, I mean, you can see that on a spectrum analyzer, is it really transmitting in the frequency that I have an experimental license? I don't really see problems with that.
The next question would.
You can also still ask questions for the previous presentation, right? I mean, we didn't have enough question time, and Dieter and Carsten are still here, yeah.
Are there any plans on wideband CDMA, or do you know anybody who wants to do this?
Yeah, well, 3G, the problem of SWORD is that the chipsets are much more, so first of all, the technology is incredibly more complex. So 3G networks, you know, if you think GSM is complex, 3G networks are much more complex. The layer 2 with GSM is extremely simple. The layer 2 of WCDMA is already, you know, this ASN1 specified monster that use packed encoding rules and has SDL specified state gate diagrams and God knows. So the complexity is bigger. I'm not saying it cannot be done. Where I see more of a practical difficulty is in running custom code on 3G baseband processors because they are typically much more locked down than the 2G chipsets. So the 2G chipsets are fairly old, and most of them, or a lot of them, do not come without any cryptographic signatures and so on. But finding a way how you can reliably, on a lot of telephones, install a code on a 3G handset, I think is definitely a different. Of course, I mean, there are exploits, you know, from the SIM card interface, from the air interface, and so on. But those are only valid against a specific firmware version of a specific phone model, and you know, and then they update the software, and the hole is closed again. So I would find myself difficult. I mean, it would be difficult for me to motivate myself to put, you know, many man-months into something where I don't really know, where I don't really have a guarantee that I can, in the end, run it reliably on a certain number of devices, and other people run it on a certain number of devices. So I don't know anyone who's working on this. For sort of the development team that's behind OsmocomBB and OpenBSC, for us the primary goal now is to have a 3G network side, to implement the network side. The telephone side is sort of yeah, sort of nice to have, but nobody's really working on this.